This is Dr. Vamsi Mohan, Professor, Department of Civil Engineering, IARE. Today, I will be discussing some numerical examples on bending theory. Already in the previous video, we have discussed the derivation of bending theory. The bending theory, which is m by I equal to f by y equal to e by r, in which m is the bending moment at any section, I is the moment of inertia or second moment of area, f the bending stress, and y the distance of layer at which the stress is f. E is Young's modulus and r is radius of curvature of the elastic curve. Okay, this derivation already discussed in the previous slides, previous video, and in this video we'll discuss some examples on bending equation. The first example reads like this: an I-section girder 200 mm wide by 300 mm deep with the flange and web thickness 20 mm is used as a simply supported beam over a span of 7 meters. The girder carries a distributed load of 5 kN per meter and a concentrated load of 20 kN at midspan. Determine the second moment of area of the cross section and the maximum stress set up in the beam. So the maximum stress will be set up at the extreme fibers, either at the bottommost or topmost fibers. Okay. So here the cross section of the beam is I section with dimensions 200 mm wide and 300 mm deep. Overall width and overall depth 200 and 300 in millimeters. Okay, the dimensions are in millimeters, and the thickness of web and flange are 20 mm each. So the beam is simply supported, okay, with the cross section in the shape of I section, and it is loaded with UDL, uniformly distributed load, of 5 kN per meter length and a point load, concentrated load at midsection of 20 kN, which is acting at midspan. Okay, so these are the loads acting on the beam. Okay, and in simply supported beam, the maximum bending moment will be at the midspan. For the given loading, the maximum bending moment will be at the midspan. So due to uniformly distributed load, the bending moment diagram will be a parabola, and due to point load, the bending moment diagram will be a triangle, okay, with the maximum ordinate at midspan. Okay, and due to UDL, the maximum bending moment at mid-span is WL square by 8, where W is UDL, intensity of UDL, and due to point load, the maximum bending moment, ordinate, will be WL by 4. The maximum ordinate of bending moment diagram will be WL by 4. This is due to point load and this is due to UDL. Okay. So now we have to find the moment of inertia of the given cross section and use that value in the equation m by I equal to f by y to find the maximum stress setup. Okay. So here we need to find maximum bending moment which occurs at mid-span. Okay. So let us see this cross section which is an I section. Okay. Now the moment of inertia of I section, we can find the moment of inertia in different ways. Okay, by considering this as a whole can be treated as a rectangle and this part, shaded part, can be subtracted. Okay, so we find the moment of inertia of entire rectangle and subtract the moment of inertia of this shaded portion so that you will get the moment of inertia of the remaining area, that is I section. That is one way. Otherwise, we divide this into 3 sections, 3 parts, 2 flange parts and 1 web. 2 flanges, bottom flange and top flange. The parts 1 and 3 represent flanges and 2 represent the web. The moment of inertia of this about the centroidal axis can be found by using parallel axis theorem. Okay. Anyway, both are correct. You will be getting the same value either way. Okay. Let us consider the first method, that is considering the rectangle as a whole of width 200 mm and depth 300 mm and subtract from that the shaded portion. Okay, the shaded portion. The moment of inertia of a rectangular section, overall rectangle, is, for a rectangle, moment of inertia about centroidal axis is BD cubed by 12. Okay, and the centroidal axis is same for both overall rectangle as well as the shaded portion and for I section also. It is the same. Okay, minus the width of shaded portion is 200 minus 20, that is 180, and depth is 300 minus 40, 20 plus 20, okay, 40, that is 260 cube by 12. So this is the moment of inertia of the I section. Okay, and its value is 1.86 the moment of inertia of rectangle, that is first one, BD cube by 12, is 4.5 into 10 power 8. And for shaded portion, that is 180 into 260 cube by 12, is 2.64 into 10 power 8 mm per, and its value comes out to be 1.86 into 10 power 8 mm per 4. That is the moment of inertia or second moment of area. Okay. Now, the maximum bending stress is given by the equation M maximum, sigma maximum or F maximum. We can use both, anyone. Okay. We can use term F or sigma for stress, bending stress, which is given as My by I, which is taken from this only. So F is My by I. Okay. Here the maximum stress we want, which occurs at midspan. So we find bending moment at midspan, which is the maximum bending moment. Y maximum means the distance of extreme fiber from the neutral axis. Okay. For I section, which is symmetric, either bottom most or top most, both are at the same distance. This is Y maximum actually. Okay. In this case, the distance is same for both topmost and bottommost fibers because it is a symmetric section. The Y maximum may be taken as the distance of either topmost or bottommost fiber. For unsymmetric sections, this distance, these two distances are not the same. In that case, we have to take the maximum value of these two. The distances of topmost or bottommost. Any one we have to consider, which is maximum. Okay. So in this case, what is bending moment? Maximum bending moment we given. Okay. For the given loading, which is UDL and point load, due to UDL, maximum bending moment is WL square by 8, and due to point load, WL by 4. The point load is at the midspan. So for that, maximum bending moment is WL by 4. Okay. So here UDL intensity W is 5 and span is 7 meters. Okay. So WL square by 8 plus point load is 20. Span is 7 again by 4. And this comes out to be, it is WL square by 8 and WL by 4. Okay. WL square by 8 and WL by 4. Yeah, this comes out to be 35 into 10 power 10 cube due to UDL, and due to point load WL by 4, 30.63 into 10 cube. Okay. Units are kilonewton meters. Okay. Kilonewton meters. So we can convert this, which comes out to be 65.63 into 10 cube kilonewton meters, which can be converted into Newton millimeters, multiplying with 10 power 6. Okay. Units are now Newton millimeters. And the other unit, other quantities, I and Y maximum also are substituted in millimeters. Okay. Millimeter units will substitute. Okay. Yeah. Now sigma maximum is obtained by substituting these values of bending moment. Okay, sigma maximum is M maximum is 65.63 into 10 cube, 65.63 into 10 cube into 10 power 6 into Y maximum is 150 millimeters. Distance of extreme fiber from neutral axis is 150 millimeters by I. I is, what is I value here? 1.86 into 10 power 8. 1.86 into 10 power. The sigma maximum value is given here. It comes out to be 51.8 Newton per mm square. 51.8 Newton per mm square. Newton per mm square. Okay? Or mega Newton per meter square. Mega Newton per meter square. Or mega pascals. Mega pascals. All are same. Newton per mm square is same as mega Newton per meter square or mega pascal, because pascal is Newton per meter square. 1 Newton per meter square is 1 pascal. Okay. So this is the maximum bending stress. Maximum bending stress. So if you draw the bending stress diagram, it varies linearly. It varies linearly. So maximum stress will be at the extreme fiber, bottommost or top. Okay. Yeah, this is sigma maximum. In this particular case, the top and bottommost layers are being at the same distance. The stress will be same at the bottommost and topmost fibers, which is 51.8 Newton per mm square. Okay. Yeah, that's how we find the bending stress by using bending equation. By using bending equation. Okay. There is a direct application of formula here. After finding the moment of inertia, just by substituting the values in the bending equation, we obtain the bending stress. Okay. Now let us consider one unsymmetric section also. Okay. The I section what you have seen is symmetric, in which the bending stress will be same at the bottommost or topmost fibers, and maximum distance also is same, bottommost and topmost fibers from neutral axis. But here in unsymmetric sections such as T section given in the problem, the neutral axis does not lie at mid height. It lies somewhere near to the top flange, because the area concentration is more here. The neutral axis or centroidal axis will be nearer to the top flange, because the concentration is more, area concentration is more at the top. Okay. So the neutral centroidal axis also is nearer to the top. Okay. So the T section dimensions are given. What is given in the problem? Let us read it. A uniform T section beam is 100 mm wide and 150 mm deep, with a flange thickness of 20 mm and web thickness of 12 mm. If the limiting bending stresses for the material of the beam are 80 meganewton per meter square in compression and 160 meganewton per meter square in tension. Find the maximum uniformly distributed load that the beam can carry over a simply supported span of 5 meters. So here the limiting stresses in compression and tension are given as 80 and 160 meganewton per meter square, and the beam is given to be a simply supported one. And what we need to find here, the uniformly distributed load, the intensity of UDL that the beam can carry over a simply supported span of 5 meters. Okay, the dimensions are given as 100 mm width and 150 mm depth, flange thickness being 25 millimeters and web thickness being 12 millimeters. Okay, so in unsymmetric sections, the first thing is to find distance of centroidal axis. Distance of centroidal axis. That you can find either from bottom fiber or top fiber. Let YB is the distance of centroidal axis from bottom fiber, bottommost layer. Okay. So again, the beam is simply supported over a span of 5 meters. Okay. And what is the UDL that we can apply? Okay. This you need to find. So that the compression maximum compressive stress does not exceed 80 megapascals. And tensile stress does not exceed 160 megapascals. Okay. Both these conditions are to be satisfied. So, first step is to find the distance of centroidal axis. Okay. And how to find? For that, first you divide this into two parts, web portion and flange portion. And now consider the bottommost fiber, the axis passing through the bottommost fiber, x1. Okay. Now, distance YB of the centroidal axis from bottommost fiber, that is axis x1, is given as A1 x1. Here we call it y1. A1 y1 plus A2 y2 by A1 plus A2. General formula is sigma A y by sigma A. There may be any number of components. Here we have two components, area 1 and area 2, flange and web. So we have taken the expression as A1 y1 plus A2 y2 by A1 plus A2. So what is A1 and what is y1? Y1 is the distance of centroid of this area from reference axis x1. Similarly, y2 is the distance of centroid of web portion from x1. Okay. So here both are rectangles. So the area is A1 is 100 into 25. That is the area of rectangle. So distance of centroid from bottom is, total depth is 150, and you subtract this distance of centroid from top, which is 12.5. Total depth of flange is 25. So from top, its centroid will be at 12.5 millimeters. So from bottom it is 150 minus 12.5. It is 137.5. Okay, plus A2. What is the area of web? So width of web is 12 mm, thickness of web is 12 mm, and depth is 150 minus 25. That is 125 into 12. Okay, and its centroid is 125 by 2. 125 is the depth by 2. Okay, that is 62.5 divided by area 1 plus area 2. Area 1 is 25 into 100. Area 2 is 125 into 12. 125 into 12. So it is 15. Okay. So YB will be 109.4. By calculating this, you will get the distance of centroidal axis from x1 axis is from bottom reference axis is 109.4 millimeters. Okay. So the distance of centroid from bottom is 109.4. Now moment of inertia of T section about the reference line, which is at a distance of 109.4. About centroidal axis actually. About centroidal axis is so 109.4 is the distance of centroidal axis from bottom. From top it is 50.6. Total depth is 150. Okay. So from top it is 50.6. Now how to find the moment of inertia of this about x-axis, centroidal axis? For that we will be using parallel axis theorem. Okay. That means I is equal to I1. That is 1 is flange, 2 is web. I1x, I call it I1 otherwise. I1, which is the centroidal moment of inertia of flange about its centroidal axis, which is nothing but BD cube by 12 for rectangle. Okay, plus A1 H1 square. This is parallax theorem. Is it? A1 means area of flange and Y1 is distance between the centroidal axis of the T section as a whole and the centroidal axis of flange portion. This is Y H1. Okay. Similarly, H2 is distance between the centroidal axis of web and centroidal axis of the section X. Okay. Plus I2 plus A2 H2 square. This is for web portion. What is I1? Width is 100, depth is 25, BD cube by 12 plus area of flange into H1. H1 means 50.6 here. Okay, 50.6 minus 12.5 because centroidal axis is 12.5 mm below top. So 50 minus 12.5, that is 40.1 square. Okay, not 40, sorry. It is 38.1. Okay. 38.1 square. This is for plate. Similarly for web, I2. I2 means centroidal moment of inertia of a web portion. So the width is 12 mm and depth is 125 mm. BD cube by 12. So it's moment of inertia, centroidal moment of inertia of web about its centroidal axis, plus area is 125 into 12 into h2 square. h2 is this distance, which is 109.4 minus 62.5, because this is 62.5. Okay, so the distance is 46.9. Okay, 46.9 square. A h square. A to h2 square. Okay, this comes out to be 7.36 into 10 power minus 6 meter power. This is actually you get in millimeter power 4. Multiplying with 10 power minus 12 to convert it into meter power 4. 1 meter is 10 power minus 3. 1 millimeter is 10 power minus 3 meters. So, moment of inertia in meter power 4 is 7.36 into 10 power 6. Okay. So, once you find moment of inertia, the next thing is bending moment. We'll find out by using bending equation. What is bending equation? M by I equal to sigma by y. M by I equal to sigma by y. So here M is obtained as for bending stress on compression side. If you consider its limiting value is bending stress limiting value is given as 80 meganewton per meter square. Okay. So considering compression side, moment of inertia is 7.36 into 10 power minus 6. 7.36 into 10 power minus 6. This is meganewton per meter square. We can convert otherwise into kilonewton actually. Kilonewton per meter square. 80 into 10 cube. Because we have we'll find my bending moment in kilonewton meter units. So convert this meganewton into kilonewton by multiplying with 10 cube by YT, topmost fiber we are considering, because compression means at the topmost fiber you will have compression. Limiting stress is sigma T, that is 80. So YT is 50.6. Distance of topmost fiber is 15.6. So you'll get this, and M2 is 160 into I is M, and you convert again this 160 into kilonewtons, and bottom fiber distance YB is 109.4. So we'll take the greater of these two values, which comes out to be 14.5 kilonewton meters. Okay, 14.5 kilonewton meters. So now using this bending moment, so this is by considering top fiber. Yeah, this is considering top fiber distance. We are getting bending moment 14.5 kilonewton meter. And again now it is tested by using bottom fiber, which is 10.76. So the greatest of these two is taken. Not greatest, it is greatest of moment. Yeah. So the bending moment considering the limiting stress in the bottom fiber, which is 160, is 10.76. So we have to limit the bending moment to 10.76. Okay. The least of these two will be taken. And using this, using the equation WL square by 8 for a simply supported beam with UDL, we will find the limiting load, limiting UDL, okay, which is 3.4 kilonewton per meter. 3.4 kilonewton per meter. Okay. For this, we can apply again the factor of safety. This is the maximum load that can be applied, and the safe load is obtained by applying some factor of safety. Okay. So with this, we conclude this session. We will discuss some more topics in the next session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.